Hello! In this video, we'll talk about advanced microarchitecture. So far we've covered three fundamental microarchitectures for the RISC processor. The single cycle, the multi-cycle, and the pipeline processor. The single cycle was the simplest. The multi-cycle broke our instructions into multiple smaller steps, and it was able to reduce the amount of hardware and share a single memory for both instructions and data, but it came with performance loss. The pipeline processor overlapped instructions and was quite a bit faster. So now let's take a look at many of the techniques used in modern processor design that make for really fast PCs and laptops and phones and servers and so on. So some of the techniques involve deeper pipelining. If a 5-stage pipeline is good, more stages might be better. Micro-operations for breaking complicated instructions into a sequence of simpler ones. Branch prediction to reduce the branch hazard. Superscalar processors that can issue more than one instruction in any cycle. Out-of-order processors that can execute the instructions in a different order to reduce the number of hazards. Register renaming is another technique to reduce hazards. Single instruction multiple data. Here we have instructions that act on many registers at once and get more work done in a single instruction. Multi-threading, where a processor can switch between several different programs running on it, interleaved. And multiprocessors, where we have many cores running all on one chip. So, in deep pipelining, many processors these days, especially high-performance processors, tend to have more than 5 clock cycles, 10 to 20, more pipe stages. So 10 to 20 pipe stages is pretty typical. And the number of pipe stages is limited by the pipeline hazards. So if you have, say, too much of a branch misprediction penalty, that may make performance get worse. It's limited by the sequencing overhead, that each pipeline stage we add adds some setup and clock to queue delay. Power, more registers and higher clock speed cost more power, and the cost of the extra hardware. So as we increase the number of pipeline stages, the cycle time goes down, but the time to execute an instruction depends on the cycle time but also the CPI, and if we get to too many stages, the CPI may actually start going up and the performance will get worse instead of better. An extreme example of this was the Pentium 4 microprocessor. Got to as many as 28 clock stages when processors were in a race selling based primarily on their clock frequency. And so more pipeline stages would allow for a higher clock frequency and therefore a higher selling price, even though the actual performance wasn't getting any better. Eventually the power consumption limited that. These processors were taking 130 watts or more, and that was unsustainable. So eventually Intel switched to the core microarchitecture, which is what we see right now, with fewer pop stages and more efficient use of them. The idea of microoperations is to decompose a complex instruction into a series of simpler instructions called microoperations. And at runtime, these complex instructions can be decoded into the microops. So this is heavily used in complex instruction set computers that you can't efficiently execute on a nice clean data path like the one we've talked about. So suppose you had a complex instruction that was load from an offset of 0 relative to a base address of S2, put the result in S1, and also post increment by 4, meaning add 4 to S2 and put it back in S2. So that's a common type of instruction in a complex instruction set computer. It could be used for accessing elements from an array and walking through the elements. We could break it into two simpler instructions. First the load word, and then the add to add 4 to the base address. So without the microops, we'd need a second write port on the register file to be able to write 2 results in a single cycle. That would make the register file larger and slower, so it's often better to break it up into these microops. In branch prediction, we take a guess of whether the branch will be taken. So if you have a backward branch, these usually occur in loops, and a loop usually executes more than once, so backward branches are mostly taken. For forward branches, you might take a look at the history of the branch to try to guess whether it's taken. If the branch was taken last time, maybe it's a good guess that it'll be taken again this time. So with good branch prediction, we can reduce the fraction of branches that require a flush, and modern branch predictors take well over 90% of branches correct. So in an ideal pipeline processor, the cycles per instruction would be 1, but branch misprediction is going to increase that CPI. So our goal is to mispredict as rarely as possible to have the minimum penalty to performance. Static branch prediction is the simplest technique. It just looks at the direction of the branch. If it's a backward branch, we could predict that it's taken. If it's a forward branch, we might predict that it's not taken. With dynamic branch prediction, we could keep track of the last several hundred or thousand branches in a piece of hardware called a branch target buffer. In that branch target buffer, we would record the destination of each branch and whether the branch was taken. Next time we encounter a branch, we would look for that destination and see if we'd encountered that branch before. If we had, we'd look for the program counter. We'd index the table with the branch target buffer with the program counter, so we'd find that branch, and then we could find from the table where it was going and whether it was taken, and not have to compute the branch again, but just guess that the same thing happened as before. With dynamic branch prediction, we can keep some history, and two examples are a 1-bit branch predictor or a 2-bit branch predictor. So suppose we had a program here that was going to add up the numbers from 1 to 10. So we'll initialize the sum in S1 to 0. We'll initialize our loop I to 0, and we'll initialize 10 into T0 for comparison. Now we'll have a for loop for I is 0 less than 10, I plus plus. So we'll check if I is greater than or equal to 10, then we go to done. Otherwise we do the body, sum equals sum plus I, and I equals I plus 1, and then jump back to the for loop. So this for loop should execute 10 times, and this branch greater than or equal to should only be taken on the 10th time. The 1-bit branch predictor would predict whether the branch was taken last time and do the same thing. So on the last branch of the loop, we'd been saying don't take, don't take, don't take, don't take. On the last branch of the loop, it would be taken. So we would mispredict the last branch of the loop for sure. But then if we came and ran this program again, it would see that last time we did take the branch. So on the first time we repeat the loop, it would also predict that we should take the branch, which was wrong. So anytime we predict wrong, with misprediction penalty, we have to flush some instructions. So the 1-bit branch predictor will be incorrect on the first and last iterations of the loop. If there are 10 iterations, it's wrong 20% of the time. In a 2-bit branch predictor, we could have a state machine like this that would say start out in maybe this weakly not taken state, and when we don't take the branch over and over, we move into this strongly not taken, and we predict to not take the branch. Then when we get to the last iteration of the loop, we do take the branch, so that brings us back into this weakly not taken state, where we still predict the next time to not take it. So this way we only mispredict on the last iteration of the branch, not on the first time we do it again. And so we get 90% accuracy instead of 80%.